Hello everyone and welcome back to this channel. This is the second video on priority queue, and just in case you didn't watch the first video, I'm going to put the link in this video description. So today we're going to be looking at a few things. The first one, we're going to be looking at the review of heap data structure, and then we're going to be validating some structures. Basically, we're going to be checking if each of those structures is a valid heap or not. Then after that, we're going to be looking at when and where is a priority queue used. Okay, and finally, we're going to be doing some complexity analysis. Okay, so we're going to be looking at the complexity of a priority queue implemented using a binary heap. Okay, so without any further ado, let's continue. So what is a heap? I explained this in the previous video, but I think reiterating it here would give us a much more solid understanding. So a heap is a tree-based data structure that satisfies the heap invariant, which can also be called the heap property. If A is a parent of B, then A is ordered with respect to B for all nodes A and B in the heap. So what does this mean? This means that the value of the parent nodes are always greater than or equal to the value of the child nodes, or vice versa, where the value of the parent nodes are always less than or equal to the value of the child nodes. So let's look at these two examples. So if you check the first one here, you will discover that the values of the parent nodes are always greater than the value of the child nodes. So 7 is greater than 6, 7 is greater than 5, and 6 is greater than 4, 6 is greater than 3. So the values of the parent nodes are always greater than the values of the child nodes. Okay, and the other way around is here, as you can see, where the value of the parent node are always less than the value of the child nodes. So if you check here, 1 is less than 3, 3 is less than 7, right? 1 is less than 2, 2 is less than 4, 2 is less than 5. So the values of the parent nodes are always less than the value of the child nodes. Okay, so this is the other way around. So the first case is called the max heap, where the value of the parent node is always greater than or equal to the value of the child nodes. And the second one here is called the mean heap, where the values of the parent nodes are always less than or equal to the value of the child nodes. Okay, so you can see this diagram here, which explains it better. Okay. Okay, so now we're going to be taking a look at some structures, and we want to know if those structures are a valid heap or not. So let's start from this, right? I'm going to give you some time to check if this is a valid heap or not. Okay, so is this a valid heap? Well, no. This is not a valid heap. Why? Because this is a minimum heap where the values of the parent should always be less than the value of the child nodes, right? And in this case, 4 is greater than -1. So this is invalid. Okay, so let's check the second one. So is this a valid heap? Well, no, this is not a valid heap. Why? Because we always expect the values of the parent node to be greater than the values of the child nodes, right? And in this case, 10 is greater than 4, which violates the heap property. So this is not a valid heap. Okay, so is this a valid heap? Sounds confusing, right? Or looks confusing? Yes, this is a valid heap. Okay, so and this is an example of a binomial heap, which is a special kind of heap, right? So if you check out these structures here, you discover that this itself satisfies the heap invariant, right? So the values of the child nodes are always greater than the value of the parent nodes, right? So this is satisfied, right? And if you check over here, you discover that okay, this is 7 greater than 4, this is 9 greater than 7. This is 8 greater than 7. So this is a mean heap, right? Okay, so this is a special kind of heap called the binomial heap. And I mean, if you want me to make a video on this, I can make a video on the types of heap that we have, because we have the binomial heap, we have the factorial heap, and we have the binary heap. Okay, so the binomial heap is used majorly when you want to merge two heaps together. Okay, so it performs that operation efficiently. Okay, so whenever you want to merge two heaps together, please take a look at the binomial heap. It does that efficiently. And if you want me to make a video on this, I mean, just put it in the comment box. I would make a video on that. But for now, let's stick to the basics. Okay, most times you find binary heap. That is the mostly used data structure for a priority queue. So is this a valid heap? Well, no, this is not a valid heap. As a matter of fact, this is not even a tree, right? So the structure contains a cycle, which makes it a graph and not a tree. Okay, so this is not a valid heap. It has a circle, but this is not a valid heap. Okay, so is this a valid heap? Yes, this is a valid heap. Why? Because the values of the child nodes is equal to the value of the parent nodes, which satisfies the heap invariant, the heap property, right? Remember, it is either maybe less than or equal to, or greater than or equal to, right? But in this case, it is equal to the child nodes, so it is a valid heap. Okay, so is this a valid heap? Well, no, this is not a valid heap. Why? As you can see, we expect the value of the child nodes to always be greater than the value of the parent node, right? But if you go down over here, you discover that the value of the child node now is less than the value of the parent node over here. So that means this structure does not satisfy the heap property. So that makes it invalid. However, if we change the structure to something like this, so you can see now that 10 was made the parent, and that automatically turns this to a valid max heap, because the child nodes has values that is less than the value of the parent node. Okay, so that makes this heap a max heap, which is valid. Okay, so is this a valid heap? Yes, this is a valid heap. Okay, this is just a heap with a single node, right? And this is how you start a node on default, right? I mean, a single value has to enter first before you add other values, right? So this is a valid heap that has a single node. Okay, so where is a priority queue used? Okay, one of the most common scenario where we use a priority queue is during the implementation of Dijkstra's shortest path algorithm. Okay, it is used to fetch the next node that we want to explore. Okay, so that's one of the the most popular ways to use a priority queue. The next one is that it is used in any best first search algorithm, such as A star. Okay, to fetch the next most promising node. Another phenomenal way to use a priority queue is for Huffman encoding, okay, which is used for lossless data compression. Okay, priority queue can also be very handy in scenarios where you want to fetch the next best or the next worst element. Okay, priority queue is also used in algorithms to find the minimum spanning tree. Okay, so just in case you want to do that, you can check out priority queue for that. Okay, you can see that priority queue is used heavily when it comes to graphs. Okay, I think one of the most popular places you use priority queue is in graphs, right? Okay, they are used in other places, but I mean majorly it's in graphs. Okay, so finally, let's take a look at the complexity of a priority queue implemented using a binary heap. So first, there exists a method that allows us to construct a binary heap from unordered array, okay, and that takes linear time, okay. That takes a linear time. I mean, I'm not going to show you that. I mean, and if you want me to make a video on that, you can just put it in the comment box, okay. And this forms the basis for a sorting algorithm called the heap sort algorithm, okay. So if you want me to make a video on that, I will make it on that, okay. But for now, just know this, okay. So the next method is the polling method, or the polling operation, that allows us to remove the element at the top of the heap, okay. And that takes log n time because we might have to reshuffle the elements or resort the elements in the heap. So the next operation is the picking operation, which allows us to check the element at the top of the heap, and that takes a constant time, which is beautiful, right? The next operation is adding, okay. So when you add a new element to the heap, it takes a log n time because we might have to reshuffle the elements in the heap to satisfy the heap invariant or the heap property. The next operation is the naive removing. Okay, so if you want to remove an element that is not at the front of the heap, it takes a linear time. I mean, if you want to do the naive removing, it takes a linear time. However, with the help of a hash table, we can achieve this operation in log n time. Okay, so we can achieve this operation in log n time with the help of a hash table. Okay, so the next operation is the naive contains, right? So if you want to check if an element is in the priority queue or not, basically you have to check all the elements one by one, and that takes a linear time, okay. However, with the help of a hash table, we can also achieve this in a constant time, right, which is beautiful. So we can I'm going to show you in the future how this can be achieved, okay. So please subscribe if you haven't subscribed, because I mean, a lot of videos are coming and I don't want you to miss out, okay. So we can achieve this operation in a constant time, but I mean, using a hash table adds adds a bit of space complexity. So using a hash table to optimize operations takes linear space, okay. That takes a linear space, and it also adds a bit of overheads, okay, to the binary heap implementation, okay. So because we have to literally store all the elements in another data structure, which is the hash table, and that takes linear space. I'm going to show you this in the future, so please stay tuned, okay. All right, everyone, that's going to be the end of this video for now. Please, if you haven't subscribed, don't forget to hit the subscribe button so that you're not going to miss out from the upcoming videos. Thanks everyone, and see you in the next video. Don't forget to subscribe, okay. Bye.